talk about the normal distribution, one of the most important distributions. So we say a continuous random variable x follows a normal distribution if its PDF f is equal to 1 over the square root of 2 pi sigma e to the negative x minus mu squared over 2 sigma squared. And the parameters that are specific to a given distribution, normal distribution, are mu and sigma. So we write x is normal, or distributed normally, mu sigma squared. And further, the expectation of x is equal to mu, and the variance of x is equal to sigma squared. So for example, if I said x was normally distributed, whose mean is 3 and sigma is 2, then the PDF for this particular normal distribution would be 1 over the square root of 2 pi times 2 e to the negative x minus 3 squared over 2 times 2 squared. Another example in the other direction, if the PDF for a continuous random variable is equal to 1 over the square root of 2 pi 7 e to the negative x minus 2 squared over 2 times 7 squared, then we see that x is a normal random variable whose mean is 2 and whose variance is 7 squared. Okay, one of our most important of the normal distributions is the standard normal. And the standard normal, often denoted with the letter z, is such that mu is equal to 0 and your variance is 1 squared. So the mean of the standard normal is 0 and the variance is 1 squared, or just 1. The graph of the standard normal looks like a bell curve centered at its mean, which is 0, and where it changes concavity is 1 standard deviation above and below 0. Okay, so this one right here is one that we will return to often. So as in earlier videos, we try to find the CDF for our particular random variable. And remember, that's going to be negative infinity up to z fz of t dt, right? So it's integrating. So if this were z right here, capital Fz of z is the accumulation of all the probabilities up to that z. Now, unlike some of the earlier distributions, we have to solve this numerically. And if you're familiar with it, the z-table is numeric integration of the CDF for z. Which is very useful. So if we want to find the probability that z is less than or equal to, let's say, 2, you would go into the z-table and you would be able to pull out that probability. All right, now consider x to be some linear transformation of the standard normal, so az plus b. Well, let's notice some things. So, and whatever this random variable is, I don't know how it's distributed, but it has mean, we'll say mu sub x, and variance sigma sub x squared. Well, then the expectation of x, or mu sub x, is equal to the expectation of a z plus b, which is equal to, as we know because of the linearity of expectation, a times the expectation of z plus b. And this right here is 0, as we noticed above, and so this is equal to b. That is, b is equal to the mean of x. So at this point, we know that if x is a linear transformation of the random variable z, it's equal to AZ plus whatever its mean is. All right? All right, and the variance of a linear transformation, AZ plus B, recall, is equal to A squared times the variance of Z, and that is 1. So A squared is equal to the variance of X, sigma squared sub X, which means sigma sub X is equal to A. So if X is a linear transformation of the random variable Z, then X is actually equal to its standard deviation times Z plus its mean. And in fact, you can go the other way. Z is equal to X minus mu sub X over sigma X. That's important down the road as well. All right, we now want to find, so if X is a linear transformation of the standard normal, then what do we know? X is equal to sigma sub X Z plus mu sub X. All right, we want to find the PDF for X. And we do that by starting with the CDF. Okay, so if I say big Fx of X, that's the probability X is less than or equal to little x. And we convert this to Z. So this is the probability sigma X Z plus mu sub X is less than or equal to X. Let's solve for Z. So the probability Z is less than or equal to X minus mu sub X over sigma sub X. And at this point, we notice that this is the CDF for Z, evaluated at X minus mu X over sigma X. So the CDF for X is equal to the CDF of Z, evaluated at X minus mu X over sigma X. And so to get the PDF, we're going to take the derivative of both sides with respect to X. That gives us what we're looking for, the PDF of X, which is going to be the PDF of Z, evaluated at X minus mu X over sigma X, times the derivative of the inside, which is 1 over sigma X. And at this point, we go, this is what gets plugged into our FZ of Z. And remember that our FZ of Z, we have to remember it is 1 over the square root of 2 pi e to the negative Z squared over 2. So we're just going to replace our Z here with this entire argument. So this should be equal to 1 over the square root of 2 pi e to the negative X minus mu X over sigma X squared over 2 times 1 over sigma X. Now if we clean this up a little bit, that's 1 over the square root of 2 pi sigma X. Move that sigma up front. And I can rewrite this as negative X minus mu X squared over 2 sigma X squared. And that is precisely the PDF of a normal distribution whose mean is mu sub X and whose standard deviation is sigma sub X. So X is normal mu X sigma sub X squared. That is, if X is a linear transformation of the standard normal, it itself is a normal distribution.